Good morning or good afternoon, depending on where you are. My name is Professor Orata. We are continuing with our thermodynamics lectures. And today we want to look at, first of all, want to introduce ourselves to the boundary layer theory. So we start by looking and thinking in terms of what we learned in terms of, for example, convection, where there was a fluid and also there was a solid boundary. And so we want to think of heat transfer between these two systems as resulting from a model where, for example, we are saying that we have the solid boundary. Say that you have the solid boundary. Of the solid boundary, and we are thinking of some fluid which is actually adhering to the surface of this liquid, adhering to the surface of this liquid, so that there's kind of a stagnant layer of fluid next to this liquid. Let's call it a stagnant layer. So this is a fluid adhering to the solid surface. Of course, there is the fluid, the general fluid in the whole system, but we are thinking of this solid wall, and we are thinking of this fluid as having adhered to this surface of this particular solid, so that heat transfer between these two systems, heat transfer between those two systems, the stagnant fluid and the solid system there, will be as a result of, most likely as a result of conduction. So should be most likely as a result of conduction. So in the model where we assume that there is a thin layer of fluid adhering or attached to the solid surface. The mode of heat transfer between those two systems, the fluid and the solid, the heat transfer will be via conduction. Mode of heat transfer is conduction. And so if we assume so, that it is conduction, so remember we have this diffuse layer, we have spoken about this in our other lectures. We still have the fluid, this area. In some of the lectures we have already discussed that, so I kindly encourage you to go through some of those lectures on heat transfers. We have discussed some of these issues there, but we're now advancing so that we move in the boundary layer theory. So what are we saying? We are saying that if the mode of heat transfer is conduction, then we can apply Fourier's heat law to account for this heat transfer. Therefore, we can apply Fourier heat law, so that in a nutshell, the rate of heat transfer, this particular system, will be minus K, and then we have the area of flow and the temperature gradient. So I repeat, this is a model where we are assuming that there is a thin layer of fluid adhering or kind of attached to the surface of the solid, so that the heat transfer between those two systems will be via conduction. And so we can apply the Fourier's law to that type of model, Now, suppose now we are saying that we have the fluid flowing. Let us think of some, the fluid flowing let's think of a case where fluid flowing over flat plate. So if we are dealing with a case where we have a fluid flowing over some flat plate, let's just look theoretically that you have these flat plates, not the good, so we have flat plate, and you have a fluid flowing over the surface of that flat plate. And in this particular case, we are assuming that we don't have any slip, there's no slip between the fluid and the plate. So we are saying that in this particular case, we can think of convection. Where the heat transferred between the two surfaces is related to some film or convection heat transfer coefficient. So assume no slip. And the fluid we have convection, heat transfer, by convection. And so we can express that transfer as Q is equals to minus HA T of the surface T of the fluid. And so where H here is film or convection heat transfer coefficient, A is the surface of flow, area of flow, and it is important to mention that this transfer coefficient is not a constant. It's not a constant the way you have, for example, Planck's constant. No, it's not a constant. It depends on the velocity and viscosity of that particular system. That is the fluid. H is not a constant, and it depends on viscosity, velocity, etc. Just to mention a few. Now, we are approaching now a very important concept. Where we have to ask ourselves, when we are talking of fluid flow, what types of fluid flow do we have? And I want you to always remember, when we are talking of fluid, we are talking of liquid, we are talking of gas. Fluid represents both liquid and gas. Note that. Always remember that. Refers to liquid or gas. So, when we are talking of fluid flow, what types of fluid flow do we have? We can have what we call the laminar flow. In the laminar flow, the fluid flows continuously without interacting with adjacent fluids. The fluid flows continuously without interacting with adjacent fluids. Of course, in practice, that becomes quite a challenge. Yes, it can flow continuously at the beginning without interacting with other adjacent fluids, but of course, as time goes by, then those interactions take place and it leads us to another type of flow. And that type of flow is called turbulent flow. And so this, before we move out of that, the laminar flow can also be referred to as a streamlined flow. Or a streamlined flow. Now, like we have said, as the fluid continues flowing, it could interact, or some changes in its internal flow dynamics can lead to certain reactions in terms of the fluid flow. For example, if we have velocity gradients developed within the fluid, then you'll have eddy currents. These are non-linear type of flows. If you remember, they are what I also call the Brownian motions. They are non-linear flows. So there could be eddy currents, and that can lead to what is called a turbulent flow. So that's the second type of flow. Second type of flow. Turbulent flow. In this particular case, as a result of velocity gradients or any other non-linear interactions in the fluid dynamics, can lead to formation of eddy currents. And so these eddy currents are non-linear. These are non-linear. And so it can create turbulence in the flow of the fluid. Remember we said the laminar flow, the fluid is flowing continuously without interacting with any adjacent fluids. But then as it traverses much longer distances, then there could develop velocity gradients within the fluid itself, or any other non-linear interactions within the fluid itself, and this can lead to a turbulent flow. This leading to a turbulent flow. Turbulent, leading to turbulence. Let's just leave it as turbulence. Now, when you have this turbulence in the fluid system, the flowing fluid, when you have those turbulence, it can lead to upwelling or mixing. It can lead to upwelling or mixing of the fluid. In that fluid. Now, we are still on the fluid flowing on the surface. In the fluid flowing on the surface. Now, what happens is that if we have a surface, let's talk of the boundary layer theory. And the one we want to talk about in particular is the velocity boundary layer. Velocity so we have our surface. Let's call that our x-axis. We have our surface. And of course, this is the we have the free stream velocity. That's the free stream velocity. So we have our fluid flowing. And it has the free stream velocity, which we call US. Now, as it flows, as our fluid flows, as it flows, and the velocity, of course, picks up, then we have development, we start developing what we call a boundary layer. Let us just capture it. Boundary layer. Notice that I want this width to be the same as that there. And so what does that mean? When I say that this width is the same as this width there, then of course the velocities are the same. And of course you notice that here the width decreasing is not the same as that one, so definitely the velocities are not the same. So initially we start off we are there. So as the velocity approaches that of the free stream, as the velocity approaches that of the free stream, let's try to get it as best as we can. At the edge of the plate, this is the edge of the plate. we start having a boundary. We start having a boundary whose thickness we can signify as sigma. And so this is the velocity boundary layer. That's the velocity boundary layer. Remember, that's the velocity boundary layer. So we have that velocity, that's the free velocity, free stream velocity. So at the edge of the plate layer, we start forming that boundary layer, and this thickness is what we have denoted as sigma. And notice that at this particular point now, its velocity is approaching that of the free stream. Maybe it's 99%, 99% in terms of approaching that of 99% equivalent for the free stream velocity. But that's not the only type of boundary layer which can form. We can have concentration boundary layer, also forming in the same manner. The same manner. The template for that discussion for velocity, for concentration and temperature, or the thermal boundary layer, are just the same. We have, in the case of concentration boundary layer, the template of the discussion is just the same. So we still have fluid flowing. Let's say the concentration here, infinity. Trying to have some portion which has the same width, in other words, approaching the same velocity, concentration in this case. Still looks to me like it's a bit small, so let's push it a bit big so that it looks like it's about the same. This is concentration. Of course, this is our x-axis. So again, profile with that and the edge there, boundary for concentration with that sigma c, the thickness of that concentration boundary will be sigma. Again, remember, like I've said here, the velocities we're assuming about the same, so it's approaching the same velocity. So as you leave the edge of the plate, then you have that boundary layer, concentration boundary layer, forming by the thickness sigma c. And similarly, when it comes to temperature, then you have thermal boundary layer. Thermal boundary layer. Let's see if this pen is better. Thermal boundary layer. Then again, the template of discussion is still the same. But for discussion, still the same, based on the same principle. Again, that's our x-axis. So, there we are. This will be sigma. Okay, the thickness of the thermal boundary layer. So we have our thermal layer. So, we have just seen the formation of these boundary layers, the formation of those boundary layers. But we want to focus a little bit on the velocity boundary layer. We look at the concentration and thermal boundary layers in later lectures. So for today, we just want to mention briefly the velocity boundary layer. And what does that mean? We are saying that when we have the fluid flowing on that surface, when you have the fluid flowing on that surface, as the velocity picks up, as the fluid continues to move and the velocity picks up, there will be an increase in shear stress between the fluid and that solid surface. So in the case of a fluid flowing over a solid surface, as the velocity of the fluid increases, as the velocity of the fluid increases, the shear stress between the fluid and the solid surface increases. This is the model by Reynolds. This is a model. That's a model by Reynolds. So that as the velocity of the fluid increases, the shear stress between the fluid and the solid surface increases. And so we can capture this in a nutshell by saying that tau, and this is tau, is proportional to the velocity. This is the dynamic viscosity. That mu there represents the dynamic viscosity. And you need to be familiar with these terms. For example, when we talked about mu, we have talked about mu JT, which is Joule-Thomson coefficient, which is another important element in refrigeration and so forth. So you need to know that these terms are used. We can talk of kappa, isothermal compressibility, and you can also have kappa as thermal conductivity, and so forth. So these symbols are being used back and forth. Gamma can be the ratio of the heat capacity, Cp over Cv. Kappa can be the ratio of the heat capacity, Cp over Cv. So it's very good to be conversant with these terms. So that it represents dynamic viscosity. Or we can also represent it, so represent tau as being equal to rho v du by dy. And of course now that is the kinematic viscosity. All these are basically captured in Newton's laws of viscosity. Newton's laws of viscosity. So we have seen, in summary, the situation where we are assuming that we have a layer of the liquid, of the fluid, attached or adhering to the surface of the solid. And so